So I'd like a way to melt steel or ceramics, and my propane forge just isn't cutting it since it only goes to around 1200 C on a good day. It's great for copper, aluminum, zinc, etc., but I need at least 15 to 1600 C to melt steel, and if I want to melt aluminum oxide, I need around 2100 C, and then magnesium oxide needs around 2900 C. You can get those kind of temperatures with a fire that's breathing pure oxygen like HHO, but the problem is that it tends to burn up most of the steel instead of just melting it. But now that I have a garage with a 220 volt outlet on a 50 amp breaker, I can move a decent bit of electricity, so I'm going to be using an arc furnace for my heating needs instead of chemical fuel. Okay, I know, everyone's seen DIY arc furnaces, and half of you watching this have probably built your own. I mean, it's really one step up from just jamming a fork in a mains outlet, but I intend to build one that's a significant improvement from the typical homemade buzz box made from a microwave transformer and some oversized pencil leads. For starters, I have no intention of spending the good years of my life sitting around holding the electrodes with my hands and trying to fine-tune the position to maintain an arc. So instead of doing that, I'll be using servo motors to control the electrode positions remotely. Also, microwave transformers make pretty crappy power supplies. Sure, they're easy to get, but by the time 700 to 800 watts is going into the primary coil, the core is pretty much saturated, so you pretty quickly run into a limit on how much power you can move. They're also a huge pain to rewind the secondary coil on. You've either got to cut through all the copper on the secondary and hammer it out and then thread new windings in, or cut open the transformer core to pop the secondary coil out, wind a new one, and then weld it back together. So let me present you with a much better alternative to the microwave transformer, the giant iron donut. These are found in 110 to 220 volt converter boxes, and because of that, they have a center tapped winding that can either have one half the winding run off a 110 volt input or have the whole thing run off a 220 volt input. Common models can take 3000 to 5000 watts into the primary before the core saturates, and winding a new secondary is extremely easy since you could practically drive a truck through the inner diameter of the toroid. Mine claims to be good for 5000 watts, and I intend to try and use all of that. For a secondary, I didn't have any thick gauge wire, but a friend of mine provided me with a big roll of 12 gauge magnet wire, so I twisted 12 strands of it together, stretched it out across his shop, and then painstakingly wound it onto the toroid. This was 36 turns, and it produced an open circuit output voltage of 27 volts when running off 220 volts AC on the primary. For an arc furnace, or DIY arc welder, since the power supply is basically the same, you typically want something like 30 to 40 volts, but I think 27 will work okay. I don't have a precision multimeter, but I ran 10 amps through the secondary and it gave me 177 millivolts, so it seems there's about 18 milliohms of resistance, at least with DC. With AC it'll be slightly higher. That probably sounds like a negligible amount of resistance, but at say 150 amps, which would be close to the theoretical max output, that's making over 400 watts of heat from I2R losses in the windings. For that reason, the transformer will live in a big metal pot filled with mineral oil. This will act as an electrical insulator, but also help keep the transformer cool. And just to keep an eye on it and make sure it's not overheating, I'll have a thermocouple in the oil that'll read out the temperature on this display. I hooked up some 2-gauge cables to the transformer output and then plugged it into 220 volts to try it out. The copper strips just weld themselves together, and it sounds like they're overloading the transformer from the secondary being short-circuited. Let's try this with proper carbon electrodes. These are 1/2 inch diameter gouging rods. I think this is probably the perfect size for this power level. So they melted the concrete floor within a couple seconds, and the transformer oil isn't even warm, so I'd say we've got a pretty solid power supply. But first, a word from our sponsor, FlexiSpot. Do you want to be one of those cool people with a standing desk? Obviously you do, so you need to get a FlexiSpot E7 Plus. Unlike a lot of the cheap, flimsy desks out there, the E7 Plus has a desktop made from real wood, and it's got 4 legs instead of 2, which have a 3-stage telescoping mechanism, and it's extremely stable. Like seriously, this thing is built like a tank. It won't wobble even if I hit it with a freaking sledgehammer. It has a weight capacity of 540 pounds, and a height adjustment range between 26 and 51 inches, with 4 different presets you can set to make it return to the same position every time. In fact, the desk is so sturdy that you can use it as a bed, so you can sleep in the same place you work, which is what everyone wants to do. I haven't left my office in 3 weeks, and I've never been happier. The Treadmill can hold up to 275 pounds and go up to a 12% incline, and it's got a remote control and Bluetooth speakers. It's also really compact, and it's got rollers so you can easily move it around or stow it away under the desk or in a small closet. It's a great way to get those steps in without having to set aside extra time for going to the gym. although I just used mine for goofing off. FlexiSpot offers a 15-year warranty and free returns for up to 30 days, so there's no risk in just trying one out. They're currently doing their Black Friday sales event with up to 80% off and a chance to get 100% free orders, and compared to their competitors, their prices offer pretty incredible value. Leave a note saying Hyperspace Pirate at checkout and use my code YTE7P50 for $50 off an E7 Plus desk or WP30 off for $30 off the Treadmill. Click the link in the description below. Let's talk a little bit about the design of the furnace. With an arc furnace, you can have either direct or indirect heating. With direct heating, the stuff being melted is part of the circuit, so you get better heat transfer. The disadvantage is that whatever you're melting has to be pretty conductive, i.e. it has to be metal. With indirect heating, you strike an arc right next to the stuff you're trying to melt. You don't get quite as much heat transfer as direct heating, but the target doesn't have to be conductive, so you can melt whatever you want, like glass or ceramics. I'm going to build my furnace to be able to do both. Let's talk about melting metal first. For this, I'll have a graphite crucible, which will be insulated in fire brick held together with a steel outer frame. The arc electrodes will be suspended from an overhead gantry that can be moved up and down. The mechanism for doing this is just a gear motor connected to a lead screw, basically the same thing as a 3D printer, except it doesn't need stepper motors. They're just dumb motors that are directly connected to a dual pole, dual throw switch to move forward or backward. The electrodes are lowered into the crucible until they make contact with the metal inside, and then the arcing happens. They'll have to be moved back and forth a little bit to strike the arc, but once everything gets nice and hot, they can be set in one position and left there. Okay, simple enough, but what about indirect heating? To accomplish that, I'll have one of the electrodes on the gantry connected to a movable x-axis and turned at a slight angle. By fine-tuning the x-axis position, I can strike an arc at the very tip of the electrodes. Once the arc is going, I can lower them down onto the glass or ceramic target to melt it. The whole thing looks like a giant 3D printer, but with a pair of extremely hot chopsticks on the business end instead of an extruder. And yes, I'm building the frame out of wood and the axis brackets out of 3D printed plastic. I know it sounds insane, but the wood and plastic parts are pretty far away from the heat, and if there's any issues with infrared radiation reaching them, I'll just wrap the affected parts in shiny foil tape and maybe cool them off with a fan. The entire crucible assembly will be tiltable, and it'll be controlled by a servo motor at the back connected to the tilt shaft by a cable drum from a garage door. I might also add a motor to uncover the lid, but I don't know if it's necessary since the pour spout is already sticking out. Now you may be wondering what's the point of making all this remote control? Well, aside from the servos allowing much more precision and consistency with the arc control, I'd kind of like to keep a safe distance from the molten liquids. If you follow my Discord or Patreon, you may have seen that a few months back I melted off a sizable chunk of skin from the top of my head when molten sodium hydroxide exploded directly in my face. The good news is I was wearing wraparound goggles and a respirator, so I still have eyes and a face, but the splatter did tremendous damage to the skin that was exposed, which needed grafts to recover. Now that was at around 400 C, whereas molten steel is close to 1600 C, so you can probably imagine what that would do to a person. Plus, you've probably seen those videos where wet steel or moisture gets dropped into a smelter. This guy literally rains molten iron. All of this makes a very strong case for staying as far from the furnace as humanly possible, thus the desire to make it remote control. Besides, it makes for more interesting YouTube content. This is the graphite crucible, and here's the fire bricks that it'll be tucked inside of to keep the heat insulated. The fire brick is really soft, and I cut out the material for the pour spout by just digging it out with a chisel without even needing a hammer. Then I weld together some angle iron for the frame. Actually, calling it welding is a bit of a stretch. It's more like a monkey crudely fusing pieces of metal together. But it was enough to keep the fire bricks fenced in. Then I added a shaft for tilting the whole assembly and a pulley, which is the same type that's used on a garage door. Now let's move on to the frame. I've cut some 2x4s and some half-inch thick plywood per the CAD design that I made, so it's just a simple matter of screwing it all together, and we've got a structure for the whole thing. The crucible assembly will be mounted on these crude brackets I welded up, with the shaft resting in the piece of angle iron that's at a 45-degree angle, forming a V. It's not quite as smooth as a shaft on a bearing, but it seems to work. This worm gear motor will wind or unwind a 1/16 inch steel cable to move the crucible pulley to pour out the molten metal. It'll be mounted on yet another 3D printed bracket, which is far enough away to be safe from thermal conduction, but it might require some shielding from infrared. Now I'll mount the X-axis motor into the Z-axis carriage, which I've mounted a pair of linear bearings on for 16mm rods, and then I'll add the lead screw nut to it. Then the T8 lead screw is added to the motor, and the X-axis rails are placed into the carriage. The Z-axis bracket is screwed to the frame and the 16mm rails are added, followed by the motor and the lead screw. The Z-axis carriage is mounted, then I put the X-axis carriage on the horizontal rails. This end stop will hold the stationary electrode too. Next I get my dual pole, dual throw momentary contact switches and wire them up as shown here. Then they're installed in a 3D printed box with some labels. My 1/2" carbon electrodes just barely fit in the tongue lugs meant for 3/0 gauge wire, but only if you remove the copper jacket first. Here's how they look mounted to the gantry. Later, the lugs from the transformer output will be attached too. Let's give it a quick run. Seems to work. Now let's try it with some power connected to the electrodes. Okay, that worked really nicely and no change in the temperature of the transformer oil, so that's good news. Let's try melting this copper scrap as a first test. Right off the bat, I'm noticing that when I try to use direct heating, the arcing is very inconsistent, and that's probably because of the irregular geometry of the copper. So I'm going to try arcing between the electrodes, but getting them as close as possible to the metal without shorting through it. I found that having some fire brick covering the top really helps with heat retention, which isn't a surprise. Now, one problem I encountered was that the electrodes were getting really hot at the base and were close to melting temperature for the ABS brackets that were holding them. So my very ham-fisted solution was to simply add a giant 12-volt blower and blast cool air directly across the electrodes. After 12 minutes of running hard, the temperature is still under 40 C, so I think that fixed the problem. After 15 minutes, I started getting this funny blue flame coming out one of the electrodes. I'm kind of curious what this is from, since I don't think it's from carbon burning off, and as far as I know, there's nothing in the crucible that should be releasing hydrocarbons. If you have any idea, let me know in the comments. There's a nice shiny puddle of molten copper at the bottom of the crucible, so I think I'm done melting. Let's pull the electrodes out and see how well the pouring mechanism works. I'm not casting anything yet, I'm just going to let that molten metal dump onto some fire bricks. Alright, not bad. That's one thing I'm very happy to be far away from. Here's the first product. It's a blob of copper. After a few days in a vinegar bath and some wire brushing, it's a shiny blob of copper. Very nice. Next, let's try some steel. Well, actually these bolts are stainless steel, but it's a pretty similar melting point. I also added a lid to the top of the crucible with a slot for the electrodes and a cutout for the pour spout. The melt took over half an hour compared to the 15 minutes it took a similar mass of copper, and while the steel did melt, I wasn't able to keep it molten long enough to pour it out, so it just made a blob at the bottom of the crucible. I couldn't get the blob out of the crucible, so unfortunately I had to break it out. I was worried this might just be a big blob of oxidized slag, but it turned out it was a solid hunk of stainless steel. You can tell it's stainless from the very weak effect on the magnet. It's attracted to the stainless, but just barely, and it's pretty easy to shake off. For comparison, here's the effect on regular steel. Let's see how much current we're drawing. This probe goes up to 1000 amps with 1 millivolt per amp on the output. I'll clamp it onto one of the output leads from the transformer and plug it into my scope, and you can see we get a peak current of 326 amps, so around 230 RMS. The open circuit voltage is 27 volts, but under load it's about 21, so I think it's reasonable to say that we've got about 4.8 kilowatts of power going into the arc. That might sound like a lot, but it's worth pointing out that the average handheld propane torch also puts out several thousand watts of heat. The key difference is that the maximum temperature of the arc furnace is dramatically higher, which is the reason I'm using it. I tried to do another stainless steel melt with a much smaller crucible to reduce the thermal inertia and heat up time, but then my transformer started smoking, and even with the leads disconnected, it sounds like it's short-circuiting. To make matters even worse, there was an oil leak going out of the garage, and it turns out the secondary was arcing to the grounded pot and actually burned a small hole in the bottom which let the oil out. Up until then, the melting was actually going pretty good, and this is how it looked after just a few minutes of running before the transformer blew up. Here you can see the spots on the secondary winding where the burn-through happened. So I got a new pot and put some leftover floor tiles at the bottom to avoid having the transformer windings in contact with conductive metal. Let's try melting down these scrap drill bits. Using a smaller crucible, I was able to melt them down and get them to pour, although not with the remote control pouring. I was worried this would just be a lump of oxide slag, but the clang sounds like solid metal. Here's how it looks after a little bit of cleanup, and here's a comparison with the stainless steel chunk showing how much more magnetic it is. Now just to be sure, let's dissect it and see if it's solid inside. Sure enough, that's a solid block of steel. I don't even see any air bubbles or voids of any sort. Let's see if I can actually get some steel to melt in the big crucible so that I can pour it out with the remote control. This time I heated it for over an hour. That sparkling effect is little bits of iron jumping off and igniting in the air. Kinda cool looking, but you don't want your face anywhere near it without protection. I could see liquid in the bottom, but there was a lot of unmelted stuff, so unfortunately I won't be pouring this steel. It really did a number on the fire bricks covering the top of the crucible too. This is the abomination that came out of the furnace. We did in fact get some melting, but only down at the very bottom of the crucible, which is kind of the same thing that happened with the stainless steel earlier. It's a pretty interesting looking object though, that makes for a good spinning top. Aside from the issue of needing more insulation, currently one of the biggest pitfalls of the arc furnace is the electrode configuration. The fact that both electrodes move together in the z-axis makes for a lot of difficulty with direct heating of non-molten material due to the irregular geometry. If I was only concerned with melting metal, this would be easy to solve by simply having the crucible be one of the electrodes so that only one carbon rod would need to be lowered into the furnace and the irregular geometry issue would be irrelevant. Another possibility would be to keep two carbon rods but have them be independently movable so that just one could plunge deep down into the conductive material while the other one just brushed the surface to make an arc. That would add a lot of complexity to the system though. I also found that it's really easy to accidentally lower the electrodes too far down where they're just shorting through the material or too far up where there's no arc at all. 200 RPM was a little too fast for the Z-axis motor, so I'll probably replace it with one of these 10 RPM motors or maybe a PWM controller. Another helpful feature would be a high voltage pilot arc similar to what TIG welders have for initiating arcs. This would be pretty easy to achieve by just using a cheap ignition coil. Okay, let's move on to something non-metallic. I'm going to try making some calcium carbide to generate acetylene. In a previous video, I did this by heating a combination of calcium oxide and charcoal with an arc, but I'm wondering if I can skip the process of making the calcium oxide and just mix the charcoal with regular limestone. This pink light is from ionized calcium. You can kind of see it in the reflection of my mask too. The pink color isn't as pronounced in the video, but in person it's very intense. Okay, let's see if we got any carbide out of that reaction. Looks like that's a no. I also didn't catch the distinct smell of calcium carbide, so I guess I'll have to make calcium oxide first. I loaded up the crucible again, this time with straight limestone, and cooked it for about 10 minutes. I'm not really sure what the flame here is, since the limestone isn't flammable. I guess there's just enough graphite being blown out and ignited to cause it. There's our glowing chunk of calcium oxide and a lot of limestone residue left on the electrodes. Once this cools, I'll mix it with some graphite and go again. I use an excess of graphite because so much of it just gets ejected out or burned off. Here's what I dumped out after about 15 minutes of heating. The loose powder didn't do anything when I put it in water, but it turned out that the big lump there that's still glowing was a solid block of almost pure calcium carbide. It bubbled off acetylene for almost 15 minutes after I threw it in the water. Let's see if I can turn some of these lava rocks from my front yard into obsidian glass. It started to pour out, but just barely, and I ended up with what looks like some sort of abstract modern art piece. The remainder of the glass was stuck in the crucible, so I guess it needed to be heated longer. I was pretty impressed with how smooth this obsidian glass was. There's no roughness whatsoever on the surface, or voids or air pockets inside the material. Let's try melting some ceramic powders. Ruby should be relatively easy to make with some aluminum and chromium oxide, although the quality will be pretty crappy on account of the highly randomized crystal structure. Looks like my electrodes are pretty much gone, so I'll go ahead and pull them out. The heating pattern was such that we're left with something resembling a beehive or an egg that just hatched. After cooling it down and washing it off, it looks pretty pink, so I think I did succeed in making ruby, although there's a lot of black slag in the melt, which I think is some carbon contamination that mixed into the molten aluminum oxide. The rocks give off a nice pink glow under UV light, so I guess the reaction was successful. I don't think these are actually worth anything, but they look cool. If aluminum oxide can melt, I should have no problem melting regular old sand, so let's give that a try. What I didn't expect was how much of the sand the furnace blew out, which covered parts of the furnace and my lawnmower nearby. Looks like once again we wound up with that funny beehive shape, although unlike the sand I melted with the HHO torch in another video, this is actually pretty hard and not easy to break apart by hand. This one also has the black slag stuff inside, which I'm almost certain is carbon falling off the electrodes and getting trapped in the melt because it only occurs at the very bottom, which is where the molten pool would have been. The thing actually holds water without leaking, so I guess I've made a really low quality glass cup. It actually took quite a bit of force to smash it apart, so the strength seems to be on par with commercial glass. Let's try something with a much higher melting point. Magnesium oxide melts at a temperature of 2850 degrees C, and if I can melt that down, I can make some incredibly durable ceramics. I'm going to mix it into a paste with some water and then dry it over the stove before I try melting it in the furnace, just to keep it in more manageable sized chunks rather than having ultra fine dry powder that'll blow all over the place like the sand did. But after more than a half an hour in the furnace, absolutely nothing seems to have happened. The magnesium oxide showed no signs of melting whatsoever. That's the first substance that's survived my arc furnace. The last thing I want to try is reducing iron oxide back to iron. Usually this happens in a blast furnace when hot carbon monoxide reacts with iron oxide and steals the oxygen off of it, but if the oxide is molten, it can be reduced by carbon. I'm going to mix about 30 grams of red iron oxide with a big excess of graphite. Similar to the carbide, I use a big excess of graphite because I'm expecting a lot of it to burn off before it has a chance to react with the rust. Like I did before, I add water to make it a paste and then preheat that paste to drive the moisture out just so that everything is in more manageable sized chunks and we don't have fine powder being blasted out. I think the reaction is working because there's molten liquid at the bottom of the crucible and it's starting to splatter out these chunks that are igniting when they hit the air, kind of like a fireworks sparkler. If the chunks were just iron oxide, they wouldn't be igniting, so I think that's actual iron that's burning. I didn't get the nice smooth chunk of metal that I was hoping for, but let's dump this out and try a magnet on it to see if anything happened. Sure enough, the chunks are attracted to a magnet, so we've succeeded in reducing the iron oxide, although the chunks are really impure and mixed with a lot of carbon. Now I can't say for certain whether we've got elemental iron or black iron oxide because both of them respond to a magnet, but either way the magnet response tells us that there's some degree of reduction because if it was still red iron oxide, the magnet would have no effect. So I think there's more convenient ways to melt metal, but an arc furnace is definitely a useful tool to have for melting glass or ceramics or other miscellaneous high temperature chemistry like making calcium carbide. With a little more insulation, switching to a single rod configuration with just a small hole on the top to maximize heat retention, and a high voltage pilot arc, this would probably be a worthwhile solution for metal melting. Although personally I'm more interested in trying a high powered induction heater since that would allow melting under vacuum or inert atmosphere. That's all for now. Thanks for watching and don't forget to check out our sponsor on FlexiSpot.com. Now I gotta go feed the dog.